Hello everyone, I am Souraja Kundu from Indian Institute of Technology, Guwahati, India. Today my presentation topic is Improved Residual Vision Transformer for CT to MRI Translation. I did this research at Iwahori Computer Vision Lab, Chubu University, Japan, under the supervision of Professor Ouchi Iwahori during May to July 2023. So the main problem statement is cross-modality image translation with domain adaptation. Accurate cross-modality image translation, like converting CT scans to MRI, while preserving the critical physiological and textural intricacies, poses a formidable challenge in medical imaging domain. This is an ill-posed inverse problem because when we want to convert one modality image to the other modality, we always are not equipped with the target modality images for training. Though here, for our purpose, we used the matched pairs of CT-MRI dataset for converting CT images into MRI images. It's all because we want to use the synthetic MRIs further for medical tasks like lymph node classification, annotation, segmentation, etc. So here comes another challenge of our research, that is the preservation of intricate features into the synthetic MRI. This precision is imperative for the utility of the synthetic MRI images in critical applications like disease diagnosis, particularly in the case of cancer detection, lymph node segmentation, etc. The main research objectives which we wanted to achieve is synthesizing MRI images from CT images. And for doing that, we chose a residual vision transformer model. There had been research on the residual vision transformer by Dalmart et al. And we improved upon different parts of the Resivit. We changed the architecture of the model and also introduced new loss functions so that we can achieve our objective of preserving fine lymph node level details in the synthetic MRI. So lymph node preservation was another objective of our research. The main contributions of our research can be summarized as we introduced a new CNN-based encoder-decoder architecture in the residual vision transformer model. We chose to improve the CNN rather than the transformer because we know that CNNs are expert at capturing fine details of the synthetic of the source modality image so that it can encode the fine details from the source modality and also reconstruct the synthetic MRI images with those intricate features. Actually, the original Resbit model had both the CNN parts and the transformer parts, and the transformer part was quite powerful. The task of transformer is to capture the contextual details. That is, it can so that it can synthesize the MRI domain images, but it was not as good in capturing the lymph node level features as we want. So we wanted to propose a new CN-based encoder-decoder architecture. Also, to preserve the lymph node level features, we introduced a new loss function called the lymph node hour loss function. The name suggests that we want to preserve the lymph nodes in the synthetic MRI, and this is a new feature loss function because the original respite model used adversarial loss function and the pixel wise loss function. So the pixel wise loss function calculates the pixel wise difference between the synthetic MRI and the real MRI, and it's not the optimal way of preserving the intricate features. That's why we have used this feature loss function, which is the lymph node hour loss function. We also presented a detailed discussion on what kind of an optimal loss function be used in the Resvit model with all of our modifications. And also because of the inherent unified nature of ResVid, we say that our model is useful in extending its application into some multimodal synthesis tasks. For example, from T1 WMRI to T2 WMRI, or PET to CT, CT to PET, MRI to PET, and so on. All of this can be achieved using our our proposed model. We now discuss the related works that have been done in the domain of image translation. It all starts with the conditional GAN by Isola et al. The conditional generative adversarial network presented a framework for image-to-image translation, and this demonstrated the potential of adversarial training for generating realistic images from different source modality to different target modality. Though this model suffered from mode collapse problem, but we can say that this started the use of CNN-based GAN models for image-to-image translation tasks. Then comes Cycle GAN by Jun-Yan Zhu et al. And the specialty of this model is that we can use unpaired dataset for training this model. That means it uses an unsupervised approach for synthesizing one modality from the source modality. And this actually addresses the problem of the requirement of large dataset. A large paired dataset is not always feasible in medical imaging tasks. So cycle can actually improve the way we can use unpaired data for synthesizing image to image. Then comes Ni et al. Tasks, which is a combination of the voxel-wise loss function with the adversarial loss function in his 2D CNN model. And this combination led to clearer images with paired dataset. This actually improved the image quality, and thus they actually played with the loss function to improve the synthetic images. And then comes Jean et al.'s work of dual cycle consistency loss. They used a 2D CNN generator and a patch GAN discriminator with this dual cycle consistency loss to synthesize MRI images from CT images. And they demonstrated the potential of CNN-based model for cross-modality translation with both paired and unpaired data. That is, they used both supervised and unsupervised approach to synthesize the MRI images from the CT images. So all of the models which I have discussed so far is CNN based. And then comes the revolutionary vision transformer by Dozovitsky et al. And this vision transformer is capable of capturing long range relationships, which is very effective in synthesizing a different modality image. We want to capture the contextual feature of the different modality also, and that's why the vision transformers are effective in that. So after the introduction of vision transformers, there have been different models combining the power of both CNN and vision transformers. These are the hybrid models, like there had been trans-CT or trans-GAN models, and these hybrid models actually showcased the power of both the CNN models and the transformer model. One of those models is this residual vision transformer, or ResVit in short, by Dalmars et al. And we worked on this residual vision transformer for our research. We also discussed the drawbacks of previous research works. We say that in the earlier CNN-based models, for example, the one by Han et al., or in the modified unit FCN by Zhao et al., they struggled to generate high quality images and often resulted in blurry outputs. This limitation hinders the practical use of these synthetic images in medical domain. So another task by Jean et al. Is the application of both supervised and unsupervised approach to synthesize MRI from CT. And Jean et al.'s CNN-based approach fell short in preserving the contextual features, which are actually critical for maintaining the structural and textural details in the translated images. So the another work by Isola et al. Is the pix-to-pix GAN, and these models faced issues related to pixel level artifacts, and they lacked global coherence in the generated images. These artifacts can affect the clinical relevance of those synthetic images, and that's why we are moving away from those pixel level loss functions to the feature loss function. And the new residual vision transformer model, which was proposed by Dalmars et al., it overcame most of the problems of earlier CNN and transformer based models. But the main problem of ResVit is that it can't preserve the specific lymph node level features in the synthetic MRI. And that's where we improved on it. We discuss in brief the original ResVit model by Dalmars et al. The generator part of the ResVit is actually of interest. The discriminator of the ResVit is a simple patch gun discriminator. And in the generator part, they used encoder, information bottleneck, and decoder. The encoder and decoder are completely CNN based. They consisted of 3 layers: convolution, batch normalization, and ReLU activation layers. The decoder is the mirror image of the encoder, and there are no skip connections as such. And this encoder and decoder will be actually responsible for capturing the details of the source modality and reconstruct it into the target modality. The specialty of this ResVit lies in the information bottleneck. This actually distills the task-specific information. And the information bottleneck consists of a stack of novel aggregated residual transformer blocks, that is the ART blocks. These ART blocks learn the contextual representation via vision transformer and synergistically fuse the CNN-based local and the transformer-based global representation. We can see that in the ART blocks, there are the normalization layers and multi-head self-attention layers stacked one behind another, and with some residual connections, they are actually capturing the textual level details. So here comes our main contributions, that is the encoder and decoder. We extended the CNN architecture of the encoder and decoder, and we used 6 stacks of convolution, batch normalization, and ReLU activation layers with 3 skip connections. And we also mirrored the structure of the encoder into the decoder with appropriate transconvolution layers. The encoder distills the fine details from the source MRI and sends it to the bottleneck network. And after the distillation throughout the ART blocks, the features are sent through the decoder to reconstruct the image. And here goes the second contribution, the lymph node hour loss function. Since, as I said, that the original ResVit uses a pixel-wise loss, and we want to preserve the fine features of the source modality into the target modality, and that's why we use the feature loss function. So this feature loss function will extract the features from the real MRI image and the synthetic MRI image and compare the features. We'll take the L2 norm of the features and decrease the loss function to improve the feature preservation into the synthetic MRI. And for the feature extraction network, we have used this novel kind of feature extraction, which is multi-scale attention based network. It uses some diluted convolutional layers, those in yellow colors, and these actually signify that it can capture the details from a larger area of the source modality image. There is this first coarse level feature extraction architecture, and in the later part there is this fine level feature extraction part. And this kind of CNN based arrangement actually resulted into good extraction of the features, and we further proceeded to take the L2 norm of the features extracted and reduced it as in the model. So here we discuss why did we choose to make those modifications in the model. As we said that CNNs are very expert at extracting the fine details of the lymph node level, and whereas the transformers are experts at preserving the textural details. So that's why we focused on improving the CNN part, that is the encoder decoder, and we proposed this new modification. And also, since we wanted to capture the fine features of the real MRI into the synthetic MRI, we use this lymph node hour loss function. It actually overcomes the performance of original pixel-wise L1 loss function because it minimizes the square difference of the features rather than the pixel values, and that helps significantly in the visual perception of the synthetic MRI rather than the pixel wise difference. So these are the reasons why we implemented those modifications into the ResVit model. Here we discuss the detailed experimental results that we achieved. We trained our modified model with both a small dataset of 311 image pairs of CT and MRI, as well as a larger dataset of 2,953 images. And we saw that even with the smaller training dataset of only 311 image pairs, our modified ResVit model, which contained the encoder-decoder modification and the loss function, it actually outperformed the original ResVit model. We measured this performance in terms of the metrics like peak signal to noise ratio, SSIM, mean square error, etc. We tested it with a non-overlapping test data set and proved that our model can work with even a limited data set, which is actually useful for medical tasks. We confirmed through ablation study that both the CNN and the transformer parts are necessary for our model, and that's why we specifically disabled some transformer parts of the model and trained the model with only the CNN and as well as the CNN with the transformer. And while training with nearly 2,950 training images, 599 testing image, and 133 validation image pair dataset, we confirmed that our ResVit with the new loss function gave the highest values of PSNR SSIM and the lowest value of MSE. So it signifies that our new loss function equipped with the ResVit model can give the best performance among all the models which were pre-existing. And it also shows, the ablation study also shows that both the pre-trained network as the pre-trained networks are not that good as the model with both the CNN and transformer modifications. We also checked how our model performed during the training. So we plotted the loss function value with different epoch values, and we saw that the version of the ResVit with the new loss function actually gave much steeper decrement of the loss function with each epoch, as we can see during the fine-tuning stage of the transformer. And also we can observe that the loss function value of the original Respeed model is more or less the highest among all of the versions. That is, we checked with only the encoder decoder modification, we checked with only the new loss function and both the modifications combined together, and we saw that the loss function actually helps much in terms of decreasing the loss over the epochs. We also checked how the PSNR value, that is peak signal to noise ratio value of the synthetic image, improves throughout the training. So we plotted the mean PSNR value with different epochs for both the pre-trained model as well as the fine-tuning of the transformer, and we saw that there is a significant improvement in the mean PSNR value compared with the original Resvit model. So here we present the visual comparison of the synthetic MRIs. So in the first two columns, there are the CT and MRI pairs. The second column consists of the target MRI images. The third column shows the synthetic MRI from the previous ResBit model. And the fourth column shows that the synthetic MRI from our proposed model. It can be visually verified that our synthetic MRIs are enriched with much finer details than the previous ResBit model's synthetic MRI, and that's where we confirmed that our modifications are better than are giving better results than the original Resvit model. These are the references of the papers which I have used for the presentation. Thank you for listening to my presentation, and if you have any questions, you can share it with me through email.